In circular motion, linear displacement velocity and acceleration. They are in the plane of the particle performing circular motion. For particle A, the linear displacement, linear velocity and linear acceleration will lie parallel to the plane, but angular displacement velocity and angular acceleration these quantities are perpendicular to the plane in which particle is performing circular motion. When particle moves from A position to B position, it inscribes an angle theta, but this theta will represent angular displacement as theta vector, which will be perpendicular to the plane in which particle is performing circular motion. With change in displacement with respect to time, angular velocity omega, its magnitude will be in the plane in which particle is performing circular motion, but omega vector will be perpendicular to the plane in which particle is performing circular motion. Depending upon the values of the angular velocity, change in angular velocity for the given time will represent angular acceleration. Suppose omega 1 bar is the initial angular velocity and omega 2 bar is the angular velocity after some time period, then the difference between omega 2 bar and omega 1 bar will be in the same direction as omega 1 and omega 2 if the value of omega 2 is greater than omega 1. Then for this difference divided by time will be the angular acceleration alpha, and its direction will be same as that of the omega 2, and it will be perpendicular to the direction of the plane in which particle is performing circular motion. But if the value of omega 2 is less than omega 1, that is initial angular velocity is greater than the final angular velocity, then in such case the direction will be opposite to the value of omega 1 and omega 2. It means that the particle is getting slowed down on the circumference of the circle. So the direction of angular acceleration, which is perpendicular to the plane, but its direction, whether it should be in upper direction or in the downward direction, will depend upon the values of initial and the final angular velocities. Now, in order to study the relationship between the linear velocity and angular velocity, linear acceleration and angular acceleration, let us consider particle performing circular motion. Suppose initially particle is present at a position on the circumference of the circle whose radius is r and center at O. As particle starts moving for a very small time interval, say delta t, then it acquires the position say B after time delta t, so that it inscribes an angle delta theta. Angle delta theta is a small angle. Now in this case, if we join the point B to point A, then let arc AB be delta S and segment AB be delta X. For smaller values of delta theta, the value of delta S is approximately equal to delta X. The value of length of arc AB will be approximately equal to the segment AB. Now, by definition, angle delta theta is given as the length of arc AB upon the radius. So delta theta will be equal to delta S upon R. But this we can write as delta theta is approximately equal to delta X upon R. So we can represent this relationship as delta X is equal to R into delta theta. Now if this change is taking place in small time interval delta t, which is small, which approaches 0, but it is not equal to 0, so let us divide both sides by delta t. It becomes delta x upon delta t, which is equal to r delta theta upon delta t. So taking the limiting values on both sides, limit delta t tends to 0, delta x upon delta t. This will be equal to limit delta t tends to 0, r delta theta upon delta t. So with this, what we can write about limit delta t tends to 0, delta x upon delta t can be written as dx upon dt, which is equal to r is the constant term. Limit delta t tends to 0, delta theta upon delta t can be written as d theta upon dt. So by definition, a rate of change of linear displacement with respect to time is linear velocity, which is equal to r times d theta upon dt is angular velocity omega. And so we get the relationship linear velocity v is equal to r times the angular velocity omega. But when we give its vector notation, direction plays a rather important role, and so here we see that from point O, r vector is directed toward the point A, toward the circumference. Linear velocity v is tangential and angular velocity is perpendicular to the plane in which particle is performing circular motion. So if we plot this omega bar at point A, then, and if we extend this r vector in forward direction, we are able to give the vector diagram as omega bar. This will be V bar and this is R. So with this, if you observe this diagram as a right hand screw rule, as we turn the screw in clockwise direction in this way, the tip of the screw is going to move in forward direction. And so with this, we are able to give the vector product as omega bar cross r bar. This will be equal to V bar. And so, as we write V is equal to r omega in terms of magnitude, in vector notation, we can write V vector is equal to omega vector cross r vector. So this is the relationship between linear velocity and angular velocity. By definition, we know that a rate of change of linear velocity is the linear acceleration and a rate of change of angular velocity is angular acceleration. So with V is equal to r omega, if we differentiate this with respect to time, then dV upon dt, this will be equal to d of dt of r omega. So dV upon dt, this will be r times d omega upon dt. So this is nothing but the linear acceleration A. This will be r times angular acceleration alpha. Again, as we have seen in case of the velocity, here linear acceleration is tangential, angular acceleration is perpendicular to the plane in which particle is performing circular motion, and the radius vector is radially outward. And so if we shift the value of alpha over here, alpha vector at this point A, then again we are able to write A vector is equal to alpha vector cross R vector. And so with this we will be able to write the expressions as V is equal to R omega and A is equal to R alpha, and in vector notation V vector is equal to omega vector cross R vector and A vector is equal to alpha vector cross R vector. As we know, for uniform circular motion, value of alpha is 0. The acceleration in the particle is only toward the center of the circle along the radius, so it will be AR. But in case of the non-uniform circular motion, as value of alpha is here, so here we see that for the particle over here, tangential acceleration is there as well as the radial acceleration is there. So these two accelerations will give you the acceleration which takes the particle along the circumference of the circle. So acceleration, as in case of non-uniform circular motion, will be tangential acceleration plus radial acceleration. Now when we are going to study about the radial acceleration, or centripetal acceleration, let us consider about particle performing uniform circular motion. O is the center of the circle, A is the initial position of the particle of the circumference of the circle, let vector AP represent the linear velocity v in its initial form. As particle starts moving, after some time, it acquires the position B. At that time, the linear velocity, which is tangential, will be represented by vector B. So here in this case, initial velocity is AP vector and velocity after time, say dt, will be BQ vector. Now for this, we'll consider the small angle as delta theta. Let us join B to A so that here we form a triangle AOB. Now let us plot this AP vector over here. So BR vector and AP vector are equal vectors and parallel vectors. AP vector is equal to BR vector. So here, let us join the tip of BR vector to the tip of the BQ vector. So here, the magnitude is V. And here also it is V. So here we are having the triangle B RBQ, and here we are having the triangle AOP. Now what we know that the angle between the two tangents is always equal to the angle between the two radii drawn to the points from where the tangents originate. And as we know, AP vector is equal to BR vector, angle between AOB and RBQ, these two angles are equal angles. Now, here we see that R and R, as they are the radii of the same circle, they are equal. V and V, these two sides are also equal. So by Similarity between two triangles.